Greetings, dear viewers. Today we'll dive into one of the most fascinating and terrifying scenarios the human mind can imagine. After our journey through 5 killer galaxies, we're moving on to an even more extreme phenomenon: quasars. Imagine an object so bright that it outshines entire galaxies. An object so powerful it can incinerate all life at distances of thousands of light years. And today we'll try to answer the question: what would happen if such a monster appeared in our solar system? Get comfortable, because this will be an unforgettable journey to the boundaries of cosmic horror and scientific understanding of the universe. Before we begin theoretically destroying our solar system, let's understand exactly what we're dealing with. The word quasar is short for quasi-stellar radio source. When astronomers first discovered these objects in the early 1960s, they were puzzled. In photographs, quasars looked like ordinary stars but emitted an incredible amount of radio waves and were located at enormous distances from Earth. Over time, scientists realized that quasars aren't stars at all. They are active nuclei of distant galaxies, whose centers are supermassive black holes. But not just black holes that are actively consuming matter at an incredible rate. The mass of such black holes can reach billions of solar masses, and sometimes even more. Here's how it works. Around the black hole at the center of a quasar, an accretion disk forms, a giant vortex of gas, dust, and torn-apart stars. Matter in this disk moves at near-light speed, heating up to temperatures of millions of degrees. Under such conditions, matter begins to emit a colossal amount of energy across all ranges of the electromagnetic spectrum, from radio waves to gamma radiation. How bright can quasars be? Imagine this. A single quasar can emit thousands of times more energy than our entire Milky Way galaxy, which contains hundreds of billions of stars. This means that if you could somehow collect the light from all the stars in our galaxy and multiply it 1,000 times, you would get the brightness of one quasar. It's simply unimaginable. But here's what's truly astounding. Despite such monstrous brightness, all this energy comes from a relatively small region of space. The active region of a quasar can be the size of our solar system or even smaller. It's like trying to cram the brightness of 1 trillion suns into the space occupied by Pluto's orbit. Quasars are also known for their relativistic jets, the most powerful streams of plasma ejected along the black hole's rotation axis at speeds close to the speed of light. These jets can extend for millions of light years into cosmic space, piercing the intergalactic medium and creating giant radio lobes. Fortunately for us, quasars are a phenomenon of the distant past of the universe. Most known quasars are located at distances of billions of light years from us, which means we see them as they were billions of years ago, when the universe was young and galaxies were just forming. In the modern universe, quasars are much rarer because most galaxies have already exhausted a significant portion of their gas available to feed their central black holes. But what if things were different? What if, for some reason, a cosmic anomaly, a rupture in space-time, intervention by a super-advanced civilization, or simply a fantastic scenario, a quasar appeared in our solar system? Let's begin exploring this terrifying scenario. Imagine that astronomers around the world begin noticing strange anomalies in space. Perhaps at first, it will be small distortions in the trajectories of distant asteroids, unexplained gravitational waves, or strange bursts of high-energy radiation from what appears to be an empty section of space beyond Pluto's orbit. Over the course of several days or weeks, the situation becomes increasingly alarming. Telescopes detect something unthinkable. A point in space begins to glow with increasing intensity. First, it's a faint glow in the X-ray range, then an ultraviolet, and then in the visible spectrum. And then comes the moment when the quasar fully materializes in our solar system. Let's say it appears at the distance of Pluto's orbit, approximately 40 astronomical units from the Sun. This seems like a safe distance, but for an object of such power, it's negligibly small. What happens in the first seconds? Light and radiation from the quasar begin spreading in all directions at the speed of light. This means we on Earth will learn about the quasar's appearance only after 5.5 hours. That's exactly how much time light needs to cover the distance from Pluto's orbit to Earth. But long before we see the quasar with our own eyes, its influence will already begin to be felt. The gravitational field of the supermassive black hole at the quasar center will immediately begin disturbing the orbits of all outer planets and Kuiper Belt objects. Pluto, Eris, Makemake, and thousands of other icy bodies will begin shifting from their orbits. After a few hours, a stream of high-energy particles, cosmic rays of unprecedented intensity, will reach the outer planets. Neptune and Uranus will be the first to experience bombardment by radiation millions of times stronger than anything they've experienced in billions of years of existence. Their upper atmospheres will begin heating, molecules will be ionized, and their magnetospheres, if they can withstand such an onslaught at all, will be distorted and deformed. Saturn, with its magnificent rings and numerous moons, will be next in the path of destruction. Ice particles in the rings will begin evaporating under harsh radiation. Titan, Saturn's largest moon with its dense atmosphere, will witness an incredible spectacle. Its sky will be illuminated by glow thousands of times more intense than Earth's auroras. Jupiter, the gas giant and protector of the inner solar system, will be the first among the large planets to meet the quasar radiation head-on. Its powerful magnetic field, the strongest in the solar system, will prove completely defenseless. Jupiter's radiation belts, already considered one of the most dangerous places in the solar system, will turn into a true hell of high-energy particles. And finally, 5.5 hours after the quasar's appearance, the radiation reaches the inner solar system. Mars, Earth, Venus, and Mercury, all of them suddenly find themselves flooded with a stream of energy incomparable to anything they've experienced before. Let's imagine what happens on Earth in these first moments. Imagine an ordinary day somewhere on Earth. People go to work, children go to school, life flows its usual course. Astronomers and scientists have been in a state of alarm for several days due to strange signals from space. But the general public doesn't yet know the scale of the approaching catastrophe. And then comes the moment X. In some part of the planet, it's currently night. People who happen to glance at the sky see something incredible. A new star has appeared in the firmament. But this isn't just a bright star. It's an object shining brighter than a full moon, possibly even brighter. Within minutes, social networks explode with messages and photographs. People around the world are in confusion and fear. But the visual spectacle is the least of evils. The first thing that happens is a massive attack of high-energy radiation on Earth's magnetosphere. Our planet is protected by a magnetic field generated by the movement of molten iron in the core. This field is usually quite effective at deflecting solar wind and cosmic rays. But radiation from a quasar is a completely different level. The magnetosphere begins to compress under the onslaught of the particle stream. Auroras, usually visible only at high latitudes, are now observed worldwide, from the equator to the poles. But this isn't a beautiful natural spectacle. It's a sign that our planet's protective shield is cracking at the seams. X-ray and gamma radiation from the quasar begins penetrating the upper layers of the atmosphere. Nitrogen and oxygen molecules are ionized, creating a cascade of chemical reactions. The ozone layer, which protects us from the sun's ultraviolet radiation, begins breaking down at a terrifying rate. Within the first hours, the intensity of ultraviolet radiation reaching Earth's surface increases hundreds of times. People outdoors during daylight begin getting sunburns within minutes. Those who were careless enough to stare at the quasar for long may receive serious retinal damage. But this is only the beginning. The electromagnetic pulse from the quasar begins affecting electronics. Satellites in orbit fail one after another. GPS systems stop working. Communication satellites fall silent. The International Space Station, if it's in orbit at this moment, receives a lethal dose of radiation. The crew, if present, is doomed. On Earth's surface, electrical grids begin experiencing overloads. Transformers explode, leaving entire regions without electricity. This is similar to a solar storm, but millions of times more powerful. Modern civilization, dependent on electricity and electronic communications, begins to collapse. By the end of the first day, the temperature on Earth's surface begins rising noticeably. The quasar, even at the distance of Pluto's orbit, radiates so much energy that it adds a significant amount of heat to what we receive from the sun, depending on the quasar's exact luminosity. The temperature could rise by several degrees or even tens of degrees. Oceans begin warming. Glaciers and ice caps at the poles melt at catastrophic rates. Sea levels begin rising. Coastal cities face the threat of flooding. But the most terrible thing is the impact on living organisms. Ultraviolet and harsher radiation penetrates deep into cells, damaging DNA. Plants that cannot hide from radiation begin wilting. Photosynthesis is disrupted. Plankton in the oceans, the foundation of the entire marine food chain, dies en masse. Animals behave strangely. Birds lose their ability to navigate due to disruption of Earth's magnetic field. Many species, especially those living in high light conditions, receive serious radiation damage. People try to take shelter. Governments declare states of emergency. People are urged to stay indoors, away from windows, preferably in basements or underground shelters. But for most of the planet's population, such shelters are unavailable. After a few days, it becomes clear that this isn't a temporary phenomenon. The quasar doesn't disappear. It remains in the sky, relentlessly pouring its destructive energy onto our defenseless planet. If humanity somehow miraculously survives the first days and weeks, even more severe trials await us. Let's examine what will happen to Earth and the solar system in the long term. First, Earth's atmosphere will begin undergoing fundamental changes. Constant bombardment by high-energy particles will lead to chemical reactions that have never occurred on such a scale. Nitrogen and oxygen in the upper atmospheric layers will be ionized, creating nitrogen oxides in enormous quantities. These nitrogen oxides will react with ozone, accelerating its destruction. Within weeks or months, the ozone layer may be completely destroyed. Without this protective layer, Harsh ultraviolet radiation from both the sun and the quasar will reach the surface unimpeded. The consequences will be catastrophic for all living things. Plants on land won't be able to survive under such radiation. Forests will begin dying. Agriculture will become impossible. Even if people can shelter indoors, the problem of food production will become critical. Oceans will turn into dead zones. Phytoplankton, which produces about half of Earth's oxygen and is the foundation of marine food chains, will die out. Coral reefs will bleach and die. Fish stocks will disappear. The entire ocean ecosystem will collapse. Temperature will continue rising. Depending on the quasar's luminosity and exact location, the average temperature on Earth could rise by tens of degrees. Polar ice caps will completely melt. Greenland and Antarctica will become ice-free for the first time in millions of years. Sea levels will rise by tens of meters, flooding coastal cities and entire countries. Coastlines will radically change. Hundreds of millions of people will be forced to leave their homes, leading to the largest migration crisis in human history. Earth's climate systems will completely destabilize. Ocean currents like the Gulf Stream, which regulate the climate of entire continents, may stop or change direction. This will lead to unpredictable and extreme weather phenomena. But let's not forget about the quasar's gravitational impact. The supermassive black hole at its center, even at the distance of Pluto's orbit, exerts significant gravitational influence on the solar system. Planetary orbits will begin shifting. The outer planets will feel this influence first. Neptune and Uranus may be thrown into more elongated orbits or even completely ejected from the solar system. The Kuiper Belt, the region of icy bodies beyond Neptune's orbit, will be completely destabilized. Billions of comets and asteroids will begin falling into the inner solar system. This will create an epoch of intense bombardment not seen since the early days of the solar system's formation, about 4 billion years ago. Earth, Mars, Venus, and Mercury will experience constant bombardment by cosmic bodies. Each collision is a potentially catastrophic event. Large asteroids can cause mass extinctions similar to the one that killed the dinosaurs 66 million years ago. But now such events will occur not once every tens of millions of years, but possibly every few years or even more frequently. Even the sun itself won't remain unaffected. The quasar's gravitational influence may disturb the Oort cloud, a spherical shell of icy bodies surrounding the solar system at a distance of about a light year from the sun. Trillions of comets may be directed toward the inner part of the system. Additionally, if the quasar continues approaching the sun or its orbit proves eccentric, gravitational interaction may ultimately lead to catastrophic consequences. Planets may collide with each other, be ejected into interstellar space, or even be swallowed by the quasar's black hole. The picture we've painted seems absolutely hopeless. But let's be optimistic for a moment and think. Is there any way humanity could survive such a catastrophe? The first and most obvious option is underground shelter. If radiation is the main immediate threat, then deep underground bunkers could provide protection. A thick layer of rock or concrete effectively blocks most types of radiation. Imagine underground cities built at depths of several hundred meters or even kilometers. These cities would be completely self-sufficient, with their own life support systems, hydroponic farms for growing food, water, and air recycling systems. Energy could be obtained from geothermal sources or nuclear reactors. Such a scenario isn't so fantastic. The technologies for creating such shelters already exist. The question is how many people could be saved and how long they could survive in such conditions. If we assume the quasar appeared suddenly without advance warning, it would be unlikely that enough shelters could be built for a significant portion of Earth's population. But if we had at least several years to prepare, millions of people could be saved. However, life underground has its problems. The psychological impact of isolation, limited space, lack of natural light, all this creates enormous stress. Additionally, any technical malfunction in life support systems could be fatal. The second option is evacuation. But where to? To Mars? To the moons of Jupiter or Saturn? Unfortunately, all these places are also in the solar system and will be affected by the quasar. Moreover, most of them are closer to the quasar's presumed position than Earth. The only real evacuation option is generation starships, enormous spacecraft capable of sustaining the lives of thousands of people over centuries or millennia of travel to another star system. But such technologies currently exist only in science fiction. The third option is to somehow neutralize or destroy the quasar. But how do you destroy an object containing a black hole with a mass of billions of suns? This goes beyond not only our current technological capabilities, but possibly beyond what's physically possible at all. Perhaps we could try to change Earth's orbit, moving it farther from the quasar. Theoretically, this is possible using a so-called planetary engine. But again, this is technology we don't have, and creating it would take decades or centuries. The fourth option is adaptation. Perhaps some forms of life on Earth could adapt to the new extreme conditions. Bacteria and archaea, especially extremophiles living in deep oceans, hot springs, or deep underground, would likely survive the catastrophe. Perhaps millions of years after the quasar's disappearance or relocation, life on Earth could recover, evolving from these surviving microorganisms. As for humanity, could we artificially modify ourselves for survival in new conditions? Genetic engineering, cybernetic enhancements, uploading consciousness to computers. These are all theoretical possibilities, but they require time for development and ethical debates that can hardly be conducted during an apocalypse. Realistically speaking, if a quasar appears in our solar system without advance warning, humanity's chances of survival are extremely small. Even if a small group of people can shelter in underground bunkers, the long-term outlook is bleak. Without a functioning biosphere, without the ability to grow food on the surface, without a stable climate, survival will be a constant struggle. Until now, we've mainly focused on Earth, but let's examine what happens to other planets and objects in the solar system. Mercury, the planet closest to the Sun, already exists in extreme conditions. The temperature on its surface fluctuates from minus 180 degrees Celsius at night to plus 430 degrees Celsius during the day. Adding radiation from the quasar will make the day side even more scorching. The surface may heat to temperatures at which rocks begin to melt. Mercury will essentially turn into a molten ball. Venus, already the hottest planet in the solar system, thanks to a powerful greenhouse effect, will become even more hellish. Its dense carbon dioxide atmosphere will absorb additional radiation, raising the surface temperature possibly to 600 degrees Celsius or higher. Any Soviet probes miraculously still functioning on the surface will instantly melt. Mars presents an interesting case. This planet already lost most of its atmosphere billions of years ago due to a weak magnetic field and solar wind. Radiation from the quasar will finish the job, finally stripping away the remnants of Mars's thin atmosphere. But interestingly, Mars may temporarily become warmer. Frozen polar caps of carbon dioxide and water ice will begin melting, possibly creating a denser atmosphere for a short time. However, without a magnetic field, this atmosphere will quickly disperse into space. The asteroid belt between Mars and Jupiter will experience intense irradiation. Icy asteroids will begin evaporating, creating temporary comet-like tails. Some asteroids may be completely destroyed by thermal stresses. Jupiter, the largest planet, will experience dramatic changes. Its powerful magnetic field will interact with the stream of charged particles from the quasar, creating auroras on an unprecedented scale. Entire hemispheres of Jupiter may glow in X-ray and ultraviolet ranges. Jupiter's atmosphere will begin heating. The famous Great Red Spot, a giant hurricane that's been raging for hundreds of years, may change or even disappear due to changing temperature gradients. New storm systems, even more powerful, may arise in the gas giant's atmosphere. Jupiter's moons will face serious problems. Io, the most volcanically active object in the solar system, may experience even more intense volcanism due to additional heating. Europa, with its subsurface ocean considered one of the most likely places to search for extraterrestrial life, will see its icy crust begin to melt. This may temporarily create conditions for life on the surface, but radiation will quickly destroy any organisms that find themselves unprotected. Ganymede and Callisto, Jupiter's other large moons also covered in ice, will begin losing their icy shells. Water will evaporate into space, possibly creating temporary thin atmospheres that will then be stripped away by radiation. Saturn and its magnificent ring system represent one of the most beautiful sights in the solar system. But under the quasar's influence, this beauty will be destroyed. The rings consist mainly of pieces of ice of various sizes, from dust particles to house-sized boulders. Under the quasar's intense radiation, this ice will begin evaporating. Over months or years, Saturn's rings may completely disappear, turning into a faint cloud of water vapor that will gradually disperse. This will be a cosmic tragedy, an object of incredible beauty that existed for millions of years will vanish before our eyes. Titan, Saturn's largest moon, possesses a dense nitrogen and methane atmosphere, as well as liquid methane lakes and seas on the surface. Under the quasar radiation's influence, this atmosphere will begin undergoing complex chemical changes. Methane will decompose, creating complex organic compounds. Temperature will rise, possibly leading to evaporation of methane lakes. Titan may temporarily become more friendly from a temperature standpoint, but radiation will make its surface deadly dangerous. Uranus and Neptune, the ice giants of the outer solar system, are closer to the quasar's presumed location and will therefore experience even more intense effects. Their atmospheres of hydrogen, helium, and methane will begin heating and expanding. Methane, which gives these planets their characteristic blue color, will decompose under ultraviolet radiation. These planets may temporarily swell, losing part of their atmospheres to space. Their rings and moons will also suffer. Triton, Neptune's largest moon, possessing active nitrogen geysers, may experience dramatic increases in this activity due to heating. But perhaps the most dramatic impact will be on the Kuiper Belt and Oort cloud. The Kuiper Belt is a region beyond Neptune's orbit populated by thousands of icy bodies, including dwarf planets like Pluto, Eris, and Makemake. If the quasar appears at the distance of Pluto's orbit or even farther, these objects will find themselves in direct proximity to it. The gravitational impact of the quasar's supermassive black hole will completely destabilize the Kuiper belt. Thousands of objects will be thrown onto new orbits. Some will fly into the inner solar system, becoming comets. Others will be ejected into interstellar space. Some may even be captured by the black hole's gravity and gradually pulled toward it. The Oort cloud, a spherical shell of icy bodies surrounding the solar system at distances from several thousand to 100,000 astronomical units from the Sun, will also be disturbed. Trillions of comets may be directed toward the inner part of the system, creating an epic of cometary bombardment that will last millions of years. And what about the Sun itself? Our star is a massive and stable object, but even it won't remain completely unaffected. The solar wind, a stream of charged particles constantly emitted by the Sun, will interact with radiation and particles from the quasar. This may create turbulence in the interplanetary medium. If the quasar is close enough or powerful enough, it may even begin pulling matter from the Sun's outer layers, creating a stream of gas directed toward the black hole. Although the Sun is massive and the loss of a small amount of mass isn't critical in the short term, in the long term, this could affect its evolution. Additionally, additional radiation from the quasar may influence solar activity, sunspots, flares, and coronal mass ejections. This will create even more unpredictable space weather for the inner solar system planets. Let's step back for a moment from apocalyptic scenarios and turn to the scientific side of the question. What can physics and astronomy tell us about such a situation? First, it's important to understand that quasars aren't isolated objects. They exist in the centers of galaxies and feed on matter from the surrounding space. If a quasar somehow appears in our solar system, it will behave differently than a quasar in a galactic center. The main question: where will the quasar get matter to sustain its activity? In a galactic center, there are enormous clouds of gas, dust, and entire stars that can be captured by the black hole's gravity and form an accretion disk. In our solar system, such resources are much scarcer. Perhaps the quasar will begin feeding on matter from the solar system itself. The asteroid belt, comets, perhaps even entire planets may be gradually pulled in and torn apart by the black hole's tidal forces. This will be a process known as tidal disruption. When an object approaches a black hole, gravitational forces on the side of the object nearest to the black hole are significantly stronger than on the far side. This difference in force, tidal force, can literally tear the object apart. Matter from the torn object then forms an accretion disk around the black hole, heats to extreme temperatures, and radiates energy. If we assume the quasar in our solar system begins actively consuming matter, this will create additional problems. Each time a planet, asteroid, or comet is torn apart and consumed, it creates a burst of radiation, X-rays and gamma rays, as well as streams of high-energy particles. Imagine this: Jupiter, the most massive planet in the solar system, slowly approaches the quasar's black hole. As it approaches, tidal forces become increasingly strong. First, Jupiter's atmosphere begins stretching toward the black hole, forming a giant tail of gas. Then the planet itself begins deforming, transforming from a sphere into an elongated ellipsoid. Finally, the critical moment arrives. Jupiter crosses the so-called Roche limit, the distance at which tidal forces exceed the gravitational attraction holding the planet together. Jupiter tears apart. Its matter forms a bright, glowing disk around the black hole. And over weeks or months as this matter is consumed, an incredibly bright radiation burst occurs. For observers on Earth, if any still exist, this would look like a second, incredibly bright sun appearing in the sky. Radiation from this event could be so intense that it would finally destroy any remnants of life on the inner solar system planets. Another interesting physical aspect is the quasars' relativistic jets. As we mentioned earlier, quasars often produce powerful plasma streams moving at near-light speed along the black hole's rotation axis. If the solar system finds itself in the path of such a jet, the consequences will be even more catastrophic. A quasar jet is essentially a beam of ultra-high energy particles focused into a narrow cone. Any object in such a jet's path will be literally vaporized. Even if we're not directly in the jet's path, but close enough, scattered radiation from it could be lethal. It's like being near a powerful searchlight. Even if the light beam isn't aimed directly at you, the reflected light is still very bright. From an astrophysics standpoint, there's another important point. Quasars influence not only through radiation, but also through so-called quasar feedback. Powerful winds and jets from quasars can push gas out of galaxies, stopping new star formation. On the solar system scale, this would mean the quasar could literally blow away planetary atmospheres, carrying matter into interstellar space. We should also consider time frames. Quasars aren't eternal objects. They're only active while there's matter to consume. A typical quasar may be active for several tens or hundreds of millions of years before exhausting available fuel. If a quasar appears in our solar system, how long will it live? This depends on how much matter is available. If it begins actively consuming planets and other objects, it may remain active for millions of years. But if available matter is scarce, it may go dark much faster. A dark quasar becomes an ordinary supermassive black hole, still an extremely dangerous object due to its enormous gravity, but not emitting intense energy. This would be some improvement to the situation, but the black hole's gravitational influence would still make the solar system unstable. After all these dark reflections, let's ask an important question. How likely is it that a quasar could actually appear in our solar system? The good news is that such a scenario is extremely, almost infinitely improbable. Let's understand why. First, quasars don't wander around the universe. They're tied to galactic centers and can't simply pick up and move to another location. A black hole with a mass of billions of suns sits in the deepest gravitational potential well of its galaxy. To tear it from there would require an event of incredible energy, perhaps a collision with another supermassive black hole. Even if such an event occurs, the black hole won't teleport to our solar system. It would have to physically cross intergalactic space, which would take millions or billions of years. We would have more than enough time to notice this and prepare. Second, the universe is enormous, and the space between stars and galaxies is mostly empty. The probability that a wandering black hole would randomly hit precisely our tiny solar system is vanishingly small. It's like accidentally hitting a specific atom in a planet-sized haystack with a needle. Third, modern quasars are located at distances of billions of light years from us. We see them as they were billions of years ago. In the modern, local universe, quasars are extremely rare. The nearest active galactic nuclei, which are similar to quasars but less bright, are located at distances of millions of light years. However, while the quasar scenario is extremely unlikely, there are other, more realistic cosmic threats worth worrying about. For example, supernovae. If a massive star in relative proximity to us, within a few dozen light years, explodes as a supernova, it will create a stream of gamma radiation and cosmic rays that could seriously damage Earth's ozone layer and cause mass extinction. The good news is that currently there are no stars in dangerous proximity to us ready to become supernovae in the near future. Even more dangerous are gamma ray bursts, the brightest electromagnetic events in the universe, occurring during the collapse of massive stars or the merger of neutron stars. If a gamma ray burst occurs in our galaxy and its beam is directed at Earth, the consequences could be catastrophic. Fortunately, gamma ray bursts are extremely rare and usually occur in very distant galaxies. A more realistic threat is collision with an asteroid or comet. Such events have occurred in Earth's past and will undoubtedly occur in the future. However, modern astronomy actively tracks potentially dangerous objects, and there are theoretical ways to deflect an asteroid if we detect it in advance. There's also the possibility of the solar system passing through an interstellar gas cloud or even a close encounter with another star, though such events are also extremely rare on human timescales. Interestingly, geological records on Earth show traces of several mass extinctions in the past, some of which may have been caused by cosmic events. For example, there's a hypothesis that the Ordovician mass extinction, about 450 million years ago, could have been caused by a gamma ray burst. If such events occurred in the past, they may occur in the future. However, the timescales of such events are enormous, millions or tens of millions of years between them. The probability that a catastrophic cosmic event will occur during our lifetimes or even during human civilization's existence is very small. Nevertheless, studying such extreme scenarios, even as improbable as a quasar appearing in the solar system, has value. It helps us better understand the physics of the universe, the nature of extreme objects and phenomena, and also the value and fragility of life on our planet. Reflecting on such catastrophic scenarios, we inevitably arrive at deeper philosophical questions about humanity's place in the universe. The universe is a place of incredible beauty, but also unimaginable danger. Quasars, black holes, supernovae, gamma ray bursts. All these phenomena remind us that space is full of forces against which humanity is absolutely defenseless. Carl Sagan, the famous astronomer and science popularizer, once said, "The Earth is a very small stage in a vast cosmic arena." Looking at our planet from a cosmic perspective as a pale blue dot in the vastness of space, we understand how small and vulnerable we are. But this vulnerability shouldn't cause despair. On the contrary, it should inspire us to value what we have and strive for knowledge and exploration of the universe. Science has given us the ability to understand the cosmos at a level that was unthinkable just a few centuries ago. We know about quasars, black holes, dark matter, and dark energy. We've sent probes to the boundaries of the solar system and beyond. We've discovered thousands of exoplanets orbiting other stars. Each new discovery expands our understanding and simultaneously reminds us how much we still don't know. The universe is full of mysteries, and each answer generates new questions. Reflections on such extreme scenarios as a quasar appearing in our solar system also make us think about humanity's future. If we want to survive as a species in the long term, We need to become a multi-planetary civilization. As long as all our eggs are in one basket, on Earth, one catastrophic event could destroy all human civilization. But if we create self-sustaining colonies on Mars, the moons of Jupiter and Saturn, and ultimately in other star systems, will become much more resilient to local catastrophes. Of course, this is easier said than done. The technological, economic, and social challenges of creating extraterrestrial colonies are enormous. But if humanity wants to have a long-term future, this may be a necessary step. There's also the question of our responsibility to other life forms on Earth. We're not the only inhabitants of this planet, but we're the only ones who possess the technology and knowledge to understand cosmic threats. Do we bear responsibility for protecting Earth's biosphere? Some philosophers and scientists speak of the concept of planetary stewardship, the idea that humanity should be Earth's custodians, protecting it not only for ourselves, but for all other species. From this perspective, our ability to understand and potentially counter cosmic threats isn't just a matter of self-preservation, but our duty to all earthly life. Reflections on quasars and other cosmic phenomena also evoke awe and wonder. Despite all the danger they represent, quasars are incredibly beautiful and important objects for understanding the universe. They are natural laboratories for studying extreme physics, gravity, relativistic effects, high-energy processes. They help us understand how galaxies formed and evolved in the early universe. They serve as beacons, allowing us to explore the intergalactic medium at enormous distances. In a sense, quasars are a connection to the ancient history of the universe. When we observe a quasar at a distance of 10 billion light-years, we see the universe as it was 10 billion years ago, just a few billion years after the Big Bang. This time travel through light is one of astronomy's most amazing properties. So, we've reached the end of our journey through one of the most catastrophic scenarios the human mind can imagine. We've envisioned how a quasar enters our solar system and traced the destructive consequences of this event, from the first moments of arrival to the long-term impact on planets, moons, and the very possibility of life. We've seen how Earth experiences massive radiation attack, how the ozone layer is destroyed, how oceans boil away, and the biosphere dies. We've observed how outer planets lose their atmospheres, how Saturn's rings evaporate, how entire planets are torn apart by the black hole's tidal forces. We've considered theoretical survival possibilities, underground shelters, interstellar ships, adaptation, and understood that humanity's chances of long-term survival in such a scenario are extremely small. We've also discussed the scientific side of the question, the physics of quasars, black holes, and extreme astrophysical processes. And importantly, we've understood that while such a scenario is almost improbable, it's not entirely impossible from a physics standpoint. But why should we even contemplate such grim and improbable scenarios? What value is there in exploring events that will almost certainly never occur? There are several answers to this question. First, such thought experiments help us better understand science. By considering extreme situations, we're forced to apply our knowledge of physics, astronomy, biology, and other sciences in unusual contexts. This deepens our understanding and can sometimes lead to new insights. Second, reflections on catastrophes help us appreciate what we have. Realizing the fragility of life on Earth, how fortunately circumstances aligned for our civilization's existence, can inspire us to better care for our planet and each other. Third, exploring hypothetical threats can help us prepare for real ones. While a quasar in the solar system is extremely unlikely, other cosmic threats, asteroids, solar storms, even distant supernovae, are more realistic. Understanding the principles of how cosmic phenomena can affect Earth is useful for assessing and preparing for real risks. Fourth, such scenarios stimulate imagination and creative thinking. Science isn't just dry facts and formulas, but also imagination, curiosity, and the desire to explore what if. Such questions have driven human progress throughout history. Finally, reflections on our place in the cosmos, whether in the context of threats or opportunities, have deep philosophical and even spiritual significance. They remind us of our connection to the universe, that we're part of something much greater than our daily lives. Carl Sagan wrote in his book Pale Blue, "Astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world." To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue, the only home we've ever known. These words especially resonate when we contemplate such catastrophic scenarios. Yes, the universe is full of dangers. Yes, humanity is fragile and vulnerable before cosmic forces. But that's precisely why we must value our existence, strive for knowledge and exploration, and work together to create a better future. Quasars, these monsters of the ancient universe, shining brighter than trillions of suns, remind us of the scale and power of the cosmos. They exist at unimaginable distances, in the distant past of the universe, and the probability of their appearance in our solar system is virtually zero. But the very possibility of imagining such a scenario shows how far human understanding of the cosmos has advanced. We live in an amazing time. For the first time in history, humanity possesses the knowledge and tools to understand the universe at a deep level. We can observe quasars at the edge of the observable universe, calculate their properties, understand the physics that governs them, and even imagine, albeit in our minds, what would happen if such an object appeared near us. But the most important thing we can take away from this mental journey is deep gratitude for our beautiful, fragile planet. Earth is an oasis of life in the cold void of space. It's protected by a magnetic field, warmed by a stable star, inhabited by an incredible diversity of life. We live in a cosmic, quiet neighborhood where catastrophic events are rare and conditions are ideal for life to flourish. Thank you for embarking with me on this fascinating, though frightening, journey. Remember, while the cosmos is full of dangers, it's also full of wonders and mysteries waiting to be discovered. Continue looking at the sky with curiosity and awe. Continue asking what-if questions. And most importantly, cherish our pale blue dot, the only home we have. Until we meet again in a universe of mysteries and discoveries. Don't forget to subscribe to the channel and like this video if you enjoyed this journey to the boundaries of cosmic horror. And next time, we'll explore other amazing and terrifying phenomena of our infinite universe. Clear skies and safe cosmos to you all.